Right, so this is the second part of a video on reversible reactions and equilibria, and in this video we're going to look at how change. So this is the second half of a video on reversible reactions, and in this we're going to look at how changing reaction conditions can affect the composition of an equilibrium. In other words, how changing the temperature, the concentration or the pressure can change the amounts of products and reactants present in an equilibrium. And this is really important for chemists, because if we're looking to use a reversible reaction in an industrial process, so for example this is the Haber process, which is used to produce ammonia. And ammonia is a wonderfully useful substance because it can be used to make fertilizer. If we're going to use this reaction, we want to produce as much ammonia as possible. So we need to manipulate the reaction to force it to produce the maximum yield of ammonia. We don't really want our ammonia breaking down to reform the reactants that we started with. We want to force the reaction to produce as much ammonia so we can make as much money from it, or from selling it, as possible. And in order to know how we might manipulate the reaction, we use something called Le Chatelier's principle. And Le Chatelier's principle says that when a change is imposed to a system at equilibrium, the equilibrium position will change to minimise the effect of the change. So, what do we mean by the equilibrium position? Well, an equilibrium position merely tells you roughly the proportion of products to reactants present at equilibrium. So, if we take this reaction down here, if we say the equilibrium position is to the right, that means we're producing more ammonia than we have hydrogen and nitrogen in the process. If we say the equilibrium is towards the left, that means we have more nitrogen and hydrogen and less ammonia. So ideally, if we're looking to use a reaction like this industrially, we really want the equilibrium position to be as far to the right as possible, so we get the maximum amount of yield. Really, Le Chatelier's principle tells you that a reaction will do the opposite of what you do to it. And you'll see how this works in the next couple of examples. So, let's see what happens. Let's imagine we change the concentration of a substance. We've mixed nitrogen with hydrogen to make ammonia, and we've allowed equilibrium to be established. Let's then say we add some hydrogen to this equilibrium system. The equilibrium sees you adding hydrogen and thinks, right, he's adding hydrogen, I'll try to remove it. So the equilibrium position does the opposite of what you're doing. You add hydrogen and the equilibrium shifts away from the substance you're adding. So you add hydrogen or you add nitrogen and the equilibrium position moves to the right. If you take ammonia away, the equilibrium thinks, he's taking ammonia away, I must replace it. So again, the equilibrium moves to the right. The same would happen in reverse. If we increased the concentration of ammonia, I don't know why we do that if we're trying to make it, but we put extra ammonia into the equilibrium would think, he's adding ammonia, I'm going to take it away. So it would move to the left-hand side. If I decreased the amount of nitrogen or the amount of hydrogen in the system, the equilibrium sees you decreasing those things and thinks, right, I'll replace them myself. so it shifts to the left. So as long as we know this about the equilibrium, we can manipulate it to make it work for us. So we add hydrogen, we add nitrogen, and that forces the equilibrium to the right. We take ammonia away, that forces the equilibrium again to the right, so you produce even more ammonia. So this is what happens when you change the concentration of substances at an equilibrium. The equilibrium acts to counteract the change you have tried. Right, let's see what happens when we change another reaction. So here's Le Chatelier's principle again, and changing temperature is a little bit trickier. If we try and increase the temperature, the equilibrium moves in the endothermic direction. So I heat it up, the equilibrium thinks, ha ha ha, I'm going to cool down, and tries to do the opposite of what I'm doing. Therefore, if I decrease the temperature, the equilibrium moves in the exothermic direction. So exothermic means releasing energy, getting hotter. So I decrease the temperature, the equilibrium moves in the exothermic direction. Now, you need to be able to interpret this with a random equilibrium that you might get given. So here's an equilibrium, okay, the reaction of nitrogen and hydrogen to make ammonia, and you're not expected to know whether the reaction is exo or endothermic, so an examiner would tell you. And the examiner would tell you like this: delta H is negative. Now, hopefully you recognise that and you see that if delta H is negative, that is exothermic. And what that's telling you is that therefore the forward reaction is exothermic. And if the forwards reaction is exothermic, the backwards reaction must be endothermic. So in this process, if the temperature, what should we do first? Temperature increases. If we increase the temperature on this system, the equilibrium thinks, I'm going to cool down. So the equilibrium moves in the endothermic direction. So it moves in the endothermic direction, which is to the left, so you produce less NH3. Okay, and I think it's important we write that down. So if temperature increases, EQ moves endo. Okay, so NH3 yield decreases. Conversely, if we use the opposite example, if the temperature increases, that's clearly not the opposite, is it? If the temperature decreases, the equilibrium thinks, he's making it cold, I'll do the opposite, I'll warm it up. So the equilibrium position moves in the exothermic direction, so you make more ammonia. So EQ moves exo, so NH3 yield increases. So if you were doing this reaction here to produce ammonia to be used for fertilizer, given this evidence, you'd be right in thinking that a low temperature would be a good idea. It would make lots of ammonia because the equilibrium position is a long way to the right, because when temperatures are low, the exothermic direction is favoured. Now you need to be able to apply this for lots and lots of random equilibria, and the only thing you need to look for is this bit of information here. Is it exo in the forward direction, or is it endo in the forward direction? And then apply it to the situation. The final condition we're going to look at changing is pressure. So, if you increase the pressure, the equilibrium attempts to drop the pressure itself. And it does this by reducing the amount of gas in there. So if I increase the pressure, the equilibrium moves in the direction of less gaseous molecules. So the equilibrium moves to less gas molecules. Okay, and conversely, if you decrease the pressure, the equilibrium wants to make more pressure, so the equilibrium moves to more gas molecules. At no point when we're dealing with pressure do we need to even remotely consider energy changes. It's got nothing to do with it. All we're doing is looking for which side has more or less gas molecules. So we're going to use the same example, the Haber process, and let's have a look at how many gas molecules are on each side. On this left-hand side, we have 1 nitrogen and 3 hydrogens. So overall, on the left, we have 4 gas molecules. On the right, we just have 2 ammonias. So, if we have an increase in pressure, which side is the equilibrium going to move to? Well, the increase in pressure, the equilibrium moves to less. So high pressure moves the equilibrium position towards the right, so you produce more ammonia. If you decrease the pressure, the equilibrium moves to where there are more gas molecules. So you lower the pressure and the equilibrium moves to the left-hand side. So, if I was doing this reaction industrially, do I want to be doing it at a low pressure or a high pressure? The answer to that is probably a high pressure, because at a high pressure the equilibrium moves to less gas molecules, and there are less gas molecules on the right, and it's the substance on the right, the ammonia, that I'll be wanting to produce. And again, you need to be able to apply this with an equilibrium that you've never seen before. And you first of all discount anything to do with energy changes if they're talking about pressure changes, and just look for the number of gas particles on either side. If you increase the pressure, the equilibrium moves to the less gas molecules. If you decrease the pressure, you're looking to move towards where there are more gas molecules. So you have to count up the gas molecules on each side. So we've looked at changing the concentration, changing the temperature, changing the pressure. How will the equilibrium position change if we add a catalyst to this reaction? So here's the Haber process again, and how would the position of the equilibrium change if a catalyst was added? And the catalyst has no effect on the equilibrium position. It doesn't change how much product is produced, and it doesn't change how much reactant there is. It does change the speed at which equilibrium is reached if you're using a catalyst at the start, but it does not change the position of the equilibrium. So all it affects is the rate of reaction. It does not affect the amount of reactant or the amount of product which will be formed. And in the next video we look at applying all these ideas to industrial processes and how we can manipulate the reactions to produce the biggest yield possible for our reactions.